I think it's time to start. So if you can share your screen, I'd like to welcome you all to this presentation by Mr. Ruiz. And it's one of the presentation by the Center of Communication Systems and Sensing. I hope that you enjoy it and you learn the most out of it. So I just give the floor to Mr. Ruiz to present his topic.
Assalamu alaikum, everyone. Welcome to my webinar. The title of my webinar today is Coexistence of Terrestrial TV Broadcasting and IMT System. And we'll cite a case study. Just to overview what I'm going to consider, the main objective of this webinar is to show you the way to compute coordination distance in the coexistence scenario of TV broadcasting and IMT services in 600 megahertz band. And but before going into coordination distance computation, I will talk about what is the current status of this band in Saudi Arabia, how it is being used, and how can we compute the interference due to presence of both TV system and IMT system. Then at the end, I will cite a case study of KSA and Qatar border. After that, we are using a tool named SEAMCAT, Spectrum Engineering Advanced Monte-Carlo Analysis Tool. This tool we are using, and this is a freeware, and we'll show you the result. At the same time, we'll take you to demonstrate the usage of SEAMCAT. Our regulator at the Kingdom, CITC, vision is as per ITU guidelines set at global level, and the vision is unlock the potential of radio communication in Saudi Arabia for a smarter and safer future. And that includes transportation, space, media, Industry 4.0. And it almost includes most of the user devices and the systems. And this is very well aligned with the Saudi Vision 2030. So what is 600 megahertz band? And what is its current use in the kingdom? Historically, it has been used for terrestrial TV broadcasting all over the world, most of the world, and in Saudi Arabia as well. The recent development is the US and Canada have already assigned this band for B71 band for using the IMT system, which was earlier used for the TV broadcasting. Colombia and Mexico are also using the IMT band, and they have deployed it. Why is that? Because the demand for terrestrial TV viewing is very low, and it's decreasing every day. It has been taken over by the satellite TV communication, which you have been using, which you are using in most of the homes. For Saudi Arabia, 95% of the TV watchers, they're using the satellite TV. Only 1% of the households view terrestrial broadcast TV. So the entire band is sparingly used for TV broadcasting and viewing. So this creates an opportunity for us to use this band for IMT services. And what is the need of this? Because the spectrum is very congested, and because of the advent of 5G, IoT devices and other systems, the spectrum demand is in very high volume. And we are using, although the IMT services are using the other higher bands, but the 600 megahertz band is sparingly used by TV transmission, TV broadcasting. So we can relocate or we can reassign the 600 megahertz band for IMT services as well. And the study is going on. ITU has its own view, and suggestions. But when you start allocating 600 megahertz band for IMT services, you need to look into the related issues and problems. The first one is maybe you are willing to go for the 600 megahertz band to be used for IMT services, but your neighboring country may not be interested or may not be ready. And node of ITU is also required to do that. What CITC's plan is that 600 megahertz band will be available in year 2021 partially, but on a gradual clearance, it will be deployed kingdom-wide. This is their plan and published. What is 600 megahertz band? This is usually used for mobile phones in 2017 as a newer band. It is used exclusively for newer technologies like LTE 4G and new radios 5G. And in US by T-Mobile, this is already under use for IMT services. This band covers two ranges, uplink and downlink. Downlink ranges from 617 to 652 megahertz, while the uplink engages 663 to 698 megahertz. Since this band is lower in radio frequency than the most of the other bands for mobile phones, lower frequency travel farther and penetrate solids and give you better coverage. This band was being used earlier by UHF TV and for the channels 38 to 51. And these are the details of how it is subdivided with 10 kilohertz guard. What is the situation in Arab world? You can see the map, and you can see that Saudi Arabia is the entire spectrum here is free. And this is sparingly used, and this is being used. The band we are talking about is in 614 to 698, which is 614 to 698. The entire band is not used. So this is an opportunity for us to use it for IMT services. And this is the frequency allocation table of Saudi Arabia. If you see that in 300 kilohertz to in the band which I'm talking about, N71 band, this the broadcasting is happening, but this is sparingly used because there is no viewership. Apart from that, about International Mobile Telecommunication, which is IMT, there's a huge requirement of spectrum, and the details are here. These are all talked about. The smart city requirement, voice requirement, smart home building, and the other several requirements. And these are the details of how people are using it for IMT. The entire globe is subdivided into 3 regions. We are part of region 1, and under region 1, if you see the if you see the allocation of 470 to 698, there's not much activity. Now, if we want to place IMT system in place of TV broadcasting, what happens? I'll give you a complete scenario. What will happen and what are the issues or what are the challenges we need to look at. This is a TV broadcasting, and there's a DTTB receiver in residential area. You receive the desired signal. Signal is clear, and you have good viewing on one side of the border. On the other side, in another country like Saudi Arabia, you have TV broadcasting, and you want to have the IMT base station in place of TV broadcasting. So what happens is you have the IMT user equipment or user, which is receiving the correct signal, but you want to remove this IMT, the TV broadcasting, and you want to have completely taken over by the IMT base station. So what happens? This IMT base station, it starts interfering with the DTTB. And apart from that, the users also, if they are very close by, they can also interact with the DTTB receiver and disturb the reception. And this user can also be affected by the TV receiver on the other side of the border. So our objective is, if we want to have on the Saudi side, we want to have the IMT system deployed, but we want to have a clear and not disturbing environment creating on the other side of the country or other side of the border. And this, we call it as coordination distance, which defines that there'll be interference-free viewing of TV, even if we replace our TV band by IMT system. So this is what the main objective is, to find the distance of the two transmitters in between, so that the reception of the TV on the other side of the border is not at all affected due to interference of IMT transmitter. Here, as a case, I have shown you one, but there may be several transmitters working in network. No, the same scenario is repeated for the entire kingdom. So we need to find, this is the distance from the border. Like if you see Kuwait, you see the border of Kuwait is here. So then there should be a certain distance, and then you can deploy the IMT systems here. And these are different combinations. The type of the environment is also very important to consider. Like rural, where not much habitat is there, and the urban, where full habitat is there. So we have categorized them as rural, urban, rural, and all. And then interface type also. Sometimes if you're talking about Tehran and Bahrain, then you have to cross over the sea. But sometimes when you talk about Kuwait and Saudi Arabia, or Kuwait and Qatar, or Kuwait and Jordan, then you have land and land interface. One of the examples you can see that one of the examples that this is the border of Kuwait and Saudi Arabia. Saudi Arabia is on this side, where there's not much habitat, but on the other side, the Kuwait side, you can see a good population living there. So this will consider as an urban type, and this will consider as a rural type. Now, how it is going to affect, we'll show you once we move forward. We'll show you the effect of these rural and urban interfaces. So what happens that we wanted to have a tool using which we can create, we can study the scenario of interference because of interferer. So what happens that this is the user, actual user, which is a victim. And why victim? Because it is being interrupted by other interferers. Ideally, he should receive a signal, a well clear signal, but it's being affected by these interferences. So what happens in a tool when for stochastic nature creation, Monte-Carlo method is applied. And what happens, randomly these interferers are generated and their effects are counted. And this method accounts both the good communication and the bad communication also. The good one is like you receive the signal well. There may be cases If the interference is too far, it may not interfere. So you may have received the signal correctly. And the one which is very clear, very near to it, then it may affect through the interference. So all these cases are accounted and averages find out according to Monte-Carlo approach. So we're looking for a system which can take care of this Monte-Carlo approach, and there is a tool available. But before going into the tool, I'd like to just repeat the same and make the problem at the very basic level, that we have one system and we have another system. The first system is the TV system. The second system is the IMT system. So what happens that it has a transmitter, it has a receiver. Ideally, it should receive the signal. But what happens when the IMT system comes in? It has a receiver also, it has a transmitter. The transmitter starts transmitting to this transmitter signal starts being received by the victim or the TV receiver, and then it starts interrupting the reception. So this is what we are considering, and we are going to create the same scenario using the tool which we are going to use. Here, the terminology is that this is desired received signal strength, which is actual signal received by the receiver, but at the same time, it's also receiving the interfered signal also. So we'll take the effect of these two and analyze the interference also. And there's a criteria, the threshold set, that under such and such level, if the interference so much, then you can consider this as a well-received signal. If the interference increases, and it is governed by the protection ratio, and I will cite that once we move on. So in order to create the system now the approach is like this. We will create one system, which is a TV system. We'll create another system, which is IMT system, and then we'll create a link also between IMT system to TV system, because this is going to create the interference. So what we do, we have taken the standard parameters, the values of the parameters for a TV system published by ITU for generic studies. So the coverage radius here is for a rural environment is 32.1 kilometer, but urban environment 12.6, and the reference, it can be seen in the reference. Antenna pattern omnidirectional we are considering to make the life easy. Channel bandwidth is 8 megahertz. I over N ratio is -10. These are all standard values. RX noise figure 7, antenna height 10 meters. Antenna pattern is this as per IT recommendation. Antenna gauge 9.5. So these are the values, and the propagation model for the environment is used as 1546-6, which is a point to multi-point propagation model. So if we consider rural environment, then we'll consider all these, and if in case of urban, we'll consider the other. Similarly, for the IMT system, the parameters are defined. The cell radius 8 kilometer in rural case and 5 kilometer in urban case. 3 sectors, we'll be using 3 sectors, 3 sectors, and the antenna pattern as suggested in the standard of ITU is this, and we are going to use this. Antenna gain is 15 dBi, and so on. And the propagation model again will be, since we are going to use the land scenario, so we'll be using the 1546 land model. So both propagation model will be the same. And now these two parameters, set of parameters, are going to create those two systems. But at the same time, there are variables which can be varied to see the effect of interference and to change, observe the change in interference. And the frequency range, in this case, the frequency range is the variable. So it starts, this is the N71 frequency band, 614 to 694 megahertz. So we'll be using a couple of frequencies like border frequencies and middle frequencies also to see the to analyze the effect. And then transmitter height will take this as 150 meters for DTB system, and IMT system 30 meters. Power will consider 67 dBm, and for IMT system 46 dBm. Number of base stations in case of IMT network, we'll consider one single cell, we can consider 7 transmitter, and we can consider 19 transmitters. And I'll show you all the outcomes. So what happens that before going into detail, let me just recap the IMT system. There may be a system which may have only a single omni cell having omnidirectional antenna. There may be a trisector based single cell. There may be one tier trisector 3GPP IMT network, and there may be 2 tiers IMT network. So these are different scenarios we have used to analyze. And this is the entire setup where you can see there is a TV transmitter and there is a receiver. This is one link which I talked about on the left side. And then there are base stations, and these are the base stations. Since this is one tier IMT network, so you can see 7 base stations. You can see 7 base stations, and there are random users created by the simulator, and these are random users. Every time you run, you will get random users created, and the entire system is considered as a complete setup to evaluate the interference levels. So this is the scenario we are going to show you over the tool. Now, what is our methodology? Our methodology to compute the coordination distance is, first we create the received signal, which is desired signal. So what should be received by the receiver? And then we'll introduce the interference and we'll read the distance. So what we do, if we take the DRSS values against the range, like you keep the transmitter at the one point and then keep changing the receiver position away from the transmitter, and this goes from 1 kilometer to 50 kilometer distance between the transmitter. Okay, so you get this curve, and then since the radius, the coverage radius is 32 kilometer in standard cases of TV transmission. So we have taken at 32 kilometers. We read we are expecting that minus 69 dBm signal strength will be available at that receiver at 32 kilometers. Since we have this is the best signal. So this should be received. But when we introduce the IMT system, what happens? Then it introduces the interference. So the interference, to calculate the interfered field, the formula is the direct field and minus by, this is the protection ratio, minus 31 dB. And this is as per the standard. This is defined by ITU that it should be not more than 31 dBm. So if you account both DRSS and 31, the value becomes of the interfered signal is minus 100 dBm. So your interference level should always be less than minus 100 dBm. So if we read from here minus 100, this is the value of the IRSS is plotted against again the same signal where your receiver is kept at 32 kilometer and away from that until 82 kilometer. So for minus 100 dBm, if we read, we get the distance as around 40 kilometers. So this is the distance between the transmitter of the TV and the transmitter of the IMT system. And this is how the coordination distance is defined. So this is the total methodology we are going to apply. Naturally, first we have to generate the DRSS, the values of DRSS. You can see the variation. The variation, we have taken different combinations of variables, like 614 megahertz is the border, lower border, and 694 is the upper border. And the transmitter height of the TV tower is changed from 150 meter to 25, 300 meters. And you can see the variation of the signal from 1 kilometer to 50 kilometer. What are the parameters used? We have used these parameters. These are standards taken from ITU recommendations. TV tower transmitter power is 67, and so on. And whatever is suggested in the standard ITU recommendation, we have used that. And if you see the interference threshold, C over I should be 31.41 dB, or C over N plus I should be 1021. So we have used the same value in the previous slide, minus 31, and we have used that and came to minus 120. The propagation model we have used 1546-6 because it's on land, both the transmitter are on the land. Now the interfered field is computed for IMT system for a single cell. The case of single cell, if you see the variation is again the transmitter height of the IMT system is changed, varied from 20, 25, and 30 meter, and you can see the variation. It's a very close range. So if you see that the minus 100 should be the threshold. If you read the value of IRSS as minus 100, then you see it could hit for the lower range and the upper range, and this will be around maybe about 38 to 39 kilometer in between. So this is the separation distance, and it's a safe distance. These are generic cases, but there are specific cases also where for which the TV towers are operating 618, 642, 682. These are the typical frequencies of TV towers. And if you see that case, then it comes out about 38 or 39 kilometer in between, approximately. Naturally, it's not very accurate. So this is the case of single cell. But if you have a network, and if you have a network of 1 trisector, 7 trisector, and 19 trisector transmitters, then this is the case. And again, the same thing. Naturally, the separation distance or the coordination distance comes out between 52 to 54 kilometers. Again, the same thing for the specific frequencies between 53 to 54 kilometers. So in general, for these standard values, what we noticed is that in case of network, it is between 52 to 54 kilometer, but in case of single cell, it is around 40 to 41, 39 kilometer. This is a specific case of KSA and Qatar border. We just want to share the outcome, but we cannot go into detail of the results or detailed analysis. We cannot share. So in this case, if you see the Qatar border, the Qatar is here and KSA is on this side. What our objective is, they have the TV tower. We want to deploy the IMT system, but at the same time, we don't want to disturb their viewing or reception. So what we did, we took the actual values. If you see the distance, almost 36 kilometers away from the habitat of Saudi side, and the coverage of these TV towers are 31.2 kilometers. So we took all these scenarios, and if you see this side also, it's almost rural, and this side, other side also, it's almost rural. So we considered rural environment, and we considered 2 TV towers, and on the other side, IMT system, and we found out that the coordination distance came out about 40 kilometers. So this means that the IMT transmitter can be placed 40 kilometers away from the TV tower. So if we go 36 kilometers border, so from the border until inside, if we go inside 4 kilometers and place our IMT tower, it's not going to affect the reception of the TV on the other side. So this is the outcome of, and it conforms with all the standards criteria set by IT. Now, how did we do that? How did we reach to that? We used a tool named Spectrum Management Advanced Monte-Carlo Analysis Tool, which is, we call it SEAMCAT. And so what I will do now, I'll give you a small brief overview how the tool looks like and what are the different options. And then later on, at the end of the talk, I will give you a demo also. Now, what is the purpose? Purpose is to create a statistical modeling of different radio interference scenarios for performing sharing and compatibility studies. This is used heavily by the European Union, and it is developed by them only. We can also have the spatial and temporal distributions of the interference. One of the features, again, any radio system can be modeled using this. There are transmitter evaluation and receiver mask. There are different libraries given, different antenna pattern libraries given, different propagation model libraries are given, and you can have your own defined antenna patterns also injecting to your own system and run this interference scenarios. Just one point to be highlighted here, it is not designed for system planning purposes. It's only for studying the interference analysis. Here's the information about the SEAMCAT, how you can reach to the SEAMCAT. It's an open source Java-based tool. But if you want to download, you have to register first, and before the download, and registration is very simple, 4 or 5 type of information is asked. Developed in Java and is available in JR format. It can be run by OpenSE option. So you have to install the runtime Java environment in your system, and then if you open the file with JE option, it will open and launch. The tool is available at this particular snapshot of the site is here, and you can see the download current official version 5.4.2, which we are using right now currently. But there is a test version also available. And it's very well, it's supported by good documentation tutorials, lots of documentations given on the website. You can download and you can go through them. Tutorials are also given. User manual is bundled with the tool. So whenever you want to access the user manual, it's bundled with the tool. You can launch and look at it. Very well supported by SEAMCAT technical group, and whatever query you have, since it is an open source tool, you can suggest your own. If you come up with some antenna pattern, new antenna pattern, you can always suggest and upload to be used by others also. It has a good feature of import and export option. Now, I want to introduce the interface of the tool. There are how to start. Naturally, the first file created is a workspace, and it has extension of SEAMCAT workspace SWS. So that houses all the definitions of the systems, but it is also supported by different libraries. Library elements are you can have receivers, transmitters, your own design receivers and transmitters, antenna link plugins. These are the plugins which you can define and then import, and you can have an online login library also. So it's a very good support. Again, you can test your system before going into the interference analysis. You can test the antenna gain models of your user-defined antenna. You can have propagation models. You can test it also. You can test a link budget. It has a link budget calculator also. You can run the link budget test also. And it has a vector scatter tool where you can collect from two different runs the interference scenarios and put them together and compare it. Lots of options are there. And at the same time, there's a help button which takes you to the user manual. And it's a good handbook having full detail of supported by the formulas and calculations used in interference analysis. Now, once the systems are created, then naturally the system has to be run, and scenario option gives you a simulation environment to be defined. You can run in debug mode and you can run in the full mode. So these are the basic options to create systems and run the analysis. Now, what I'm going to do here, I'm going to consider a VIC-10 system, which is a TV system, and an IMT system, which is going to interfere to the TV receiver. So this is the scenario we are going to create, and we'll see how we move. First thing we need to create, compute is we need to create the transmitter of the TV system. So how the TV system transmitter is created, we can create a generic transmitter system where one of the system has one of the option as transmitter. So you can go and create the transmitter. This will be by default. This will be created by the system, or you can change also from the library. If you want to change your transmitter, you can change it, and the details of the site. See the antenna patterns identification. You can define. You can plug in other values also. You can define the frequency, and you can define the power of the system. You can define the local environment, the transmitter height. All these parameters are variables are going to be defined. So, and then next you have to define the receiver part. Receiver part again, there are different parameters. There are different variables we need to define, and we need to. What we have in our case, what we have done is we have used standard values or parameters and variables, which I have shown you in the earlier slide. So once these two things are defined, then you have to. The third one is the position and modeling, where you are going to choose the propagation model. You have to define the propagation model. There are several propagation models given, supported by the tool. You can select one of them. And then the other parameters like delta X and delta Y, because you can place the system according to your choice. And then you can also correlate putting the receiver with respect to the transmitter, so that it's easy to track where the receiver location is. Similarly, you have to create the IMT system. Again, the transmitter, it has different type of, if you see the base station is different type, you can select these base stations are IMT systems from the library supported by the tool itself. You have to put the environment. Environment may be indoor or outdoor. In our case, it is always outdoor, so we have taken 100% outdoor. And the height of the IMT transmitter is 30 meters, which is a standard. And the mask and several things, frequency you have to define. Then again, the receiver has to be defined, and it has got certain parameters. Certain parameters are suggested by the system itself, so you don't have to worry about only few parameters. If you change, it can give you a very reasonable result. And then again, the positioning and propagation, naturally propagation model, in our case, it is LAN, so we are using the 1546-6. And you can define your network. How you can define, these are the options given. I will show you when I'm going to show you the demo with different selections that your IMT network can change and accordingly. Cell radius, naturally, you have to choose the cell radius depending on the environment you have chosen. In my case, if you see the rural environment chosen, so I have chosen 8 kilometers, but accordingly you can change the selections. Now, what is the system layout? Once you go for the single tier, you can see the transmitters here, transmitter base stations. These are the base stations, and this is the reference cell. The center is the reference cell. If you want to consider this transmitter, then you can change the reference to this, and that option is there also. So once your both the systems are defined, the TV system and the IMT system, then you have to create a scenario. And there you have to consider the TV system as a vexing system. So you have to create a link which is going to create the interference from the IMT system to the TV system. And this option is given. You can have create a new link, or you can bring in the new link or link definition which you have exported from the library. And again, the certain parameters and the propagation model in between should also be the same. So we have chosen the same. If you see the type of the scenario is rural, because we have taken no clutter is used, because clutter is not going to affect much in this case. We are using the standard value. So once these three are defined, then we are ready. Our setup is ready to run for simulation. Now I will take you to the simulation steps. The first step of the simulation is to generate the DRSS, the desired received signal strength, and this is how it is done. That this is the TV transmitter, this is a TV transmitter, and this is the TV receiver. Sorry, this is the TV transmitter, and the blue lines are TV receivers. The legend is given here also. So what we have done, since we want to create from 1 kilometer to 50 kilometers, so we have changed slowly our receiver of the TV 1, 2, 3, 5, 4, 5 until 50 kilometers, so that we compute the value of DRSS and plot it against the range. But at the same time, these interfering links, transmitter and receivers are also placed. But they are not going to affect, since we are only considered about the received signal. Once we start considering the interfering signal, then they will come into picture. Next step will be, if we consider the IMT network simulation, then this is a situation. And if you see that DRSS here is constant, because your receiver is kept at 32.1 kilometer at the boundary of the TV transmitter, which is the maximum distance. And your IRSS, unwanted IRSS, which is the interfered signal, you see the random generation of computed IRSS values. And then on the basis of that, if you see the information is summarized here also on the screen. I'm not sure whether it is readable or not. DRSS, it has a mean and mean, because the value is not changing, so it remains the same, and standard deviation is 0. But the IRSS will change. Once you see the system under demo, then you will realize that. Then comes the last part, which is the interference analysis. It has a very good support of interference analysis, and we need to define that what is the criteria, C over I. Or there are 4 different criteria here. If you see C over I, C over N plus I over N, and I over N. You can choose either of them. I'll show you how to choose, and the others get computed automatically. So if you see the plot of C over I, which is unwanted, this is the DRSS in our case C, and IRSS in our case I. And if you see the variation of C over I, this is the threshold. This is the threshold, and so until here there is no interference. It's not going to affect. But after this will be affected, so we have to take care of that. And there comes the coordination distance. that you have to adjust your distance in such a way that the whole thing comes under this. Until that distance, until this distance, the coordination is, there will be no interference, but after this, there will be interference. And this can be generated. All these results are created in the vector format and can be downloaded for further processing if you want to do on your own. So this stops here, the cycle of computing the interference level. Now, I will take you, if you have any question, you please ask me so that we clarify and then we move to the.
Mr. Bilqis, thank you for the excellent presentation. How much time do you think is remaining for the demo?
I can finish in 10 minutes.
Can you make it shorter because we?
Yes, 5 minutes.
Okay.
5 minutes also I'll take you because
So
I have already defined.
Okay, so then we can have questions if you.
Okay. So let me open the tool. Okay, is my screen visible? Can you read it?
Yes, I can. I do not others, but I have a big display.
Oh, okay. So I'll as I mentioned, I'll give you two scenarios. One network. Let me look at the network only. So in the network, we have taken a TV system, and this TV system is created. As I said, we create the transmitter. So once we can add from here the transmitter, or if we want to have the library. So you can always create a transmitter and define the parameters. As I said, that you can define the parameter. You have to select the frequency. In this case, I have taken the lower band, 614 megahertz, and then the power of the transmitter can be defined here, 67 dBm power, and the mask also can be defined. This is how it has been defined. The emission floor can also be defined. And other options like local environment, as I said, indoor or outdoor. And if you click on that, you are given a distribution support, and you can have a user defined, or you can have a discrete form with a variation. But we have taken a constant, and the transmitter height is 150 meters considered in this case. And similarly, the receiver is defined. If you see the receiver antenna peak gain, dBi 9.15, the pattern is defined, and naturally the frequency has to be same as the transmitter, and the reception bandwidth. And the reception bandwidth of the receiver is 8 megahertz. Other parameters are also defined. And for the interference criteria, as I mentioned, this is 31.41 defined and -10. But it can be, either of the criteria can be plugged in and the other will be calculated. So once if I enter 31.41, the other three will be calculated. They're all interrelated. Okay, and once the receiver is defined, then we go in position and propagation model. We define the propagation model. Propagation model is defined. If you click, there's lots of support of propagation models. We are using 1546 because the land model. And then the type of general environment around the RX. We have taken the rural because the environment is rural, but you can choose suburban, urban, or a dense urban. We have taken rural on both sides. Again, the system layout. So here is the transmitter and here is the receiver. This is the TV tower. Now for the IMT system, the similar thing, we define the transmitter, but here the parameters are different. If you see, the frequency is going to be the same. And the model, if you see, the model is chosen as per standard. And okay, emission mask also can be defined. If you see the details, this is the emission mask. This is a user defined. You can always define according to your choice. It has 2 levels, but you can have multiple levels. Again, the positioning of the network. Right now, it is chosen as a single cell and the tri-sector. If I want to choose only single cell but omni, then it will change to omni, so there's no sector. Similarly, if I go to 1 tier and it is omni, but if you want to have the 3-sector, you can have the 3-sector. Like I mentioned earlier, this is the base. This is at the center. It is considered as the main. But if you want to link here, you can always change the position of the facing transmitter. At the same time, if you go to 2 tiers, you can have the 2-tier network. And here also you can see the 17 transmitters up there. You can have a wraparound also, generate wraparound also. It generates the wraparound. For the time being, we have I have used 1 tier. I'm showing you 1 tier, and the simulation, how to simulate. If you see, go and see the system layout. The system layout of the chosen IMT network is seen like this, and these are the legend. The cell and the base stations are dotted here. The blue ones, the dots, and reference cell. Since I have chosen the right word, then it is chosen here. I can change this to middle, and then it will show you the base or the main reference. So this way, both the systems are defined. Once the systems are defined, then you move from system to scenario. And scenario, you have to define a link. A link can be added from here, plus sign, or you can import. You can bring the link from outside, which is already exported from here. So if the moment you choose a plus, it gives you option. Since our victim system is already defined, so this is cannot be chosen. So the other person, but you may have more than one link, and then you have a choice of choosing that this one or that one. So I have chosen this as a link. So this is the interfering link, and you can see that interfering link, on the left side, this is it's very lightly written, but these are the interfering links which we are defining now. And the placement of the interfering link also, you have a correlated mode and you have uncorrelated positioning. Correlated means correlation with respect to a reference component is either is VSL or the victim transmitter. So what we have taken is a victim transmitter considered as a starting point. And for running, once this is ready, then you can start running. You can run the simulation. But before running the simulation, if you want to see the consistency of the system, you have given this option. If you make a mistake somewhere, then it will give you an option that you have made a mistake. Let me just change one of the frequencies, 630, and check the consistency, and it gives you an error and highlights also that where the mistake is. So you go back and correct it. check the consistency, and then it has the simulation control has got a debug mode also. It has got a full mode, and a number of events has to be good enough to cover, because it's going to randomly generate the users. So these users can be repeated also. So we should have enough number of events so that the entire area is covered and not left out. Usually it is selected. If you don't select anything, it will give you 20,000 events. But right now, to save the time, 2,000 is selected. And if you want to see in debug mode, how does it behave, and you can see that.
So Ravizia, just watch the time because it's already
yeah, just 1 minute, one more minute.
Okay.
So it gives you the complete detail of the calculation, how it has calculated. And this is only for one event. But at the same time, and you can see the results also. I have a previous run result. Let me show it to you. This is the run of the network part. The results are given. If you see that this is for the DTTB system, this is for IMT systems, and these are the stats, and the details are given here. But at the same, what I want to show you, you can download the result in complete detail in numbers in different formats: HTML format, XML format, XLS format, XLX format. So I have downloaded 2 of the files. I'll open one of the file and show you how once you download, what happens. So this generates the Excel file, and it gives you a complete detail of all events with calculations. This is a CII event, and here, if you change the criteria like I over N and compute, then it gives you the value of then. And these plots can be taken away from are saved for your further use. And what are the details of the event? See, 2,000 values we have run, and the criteria is 31.41, which is the standard. According to this, until here, it is safe to have the system, and after this, the interference will appear. Let me show you. You can run event by event also. The details of how it has computed, you can see the details. Let me go to VLT and the receiver, and you get all the details. See, the position of the receiver is, this is the first position, 32.1 kilometer it is placed, and the values, path loss is 144.251, and the further antenna height was chosen 150. So all details, and every connection will give you the details. Every connection will give you the details that. So all these vectors are, when you export the file or when you export the results, all these details are taken to Excel file. Let me show you one of the Excel files so that you have a feel.
Parviza, your 1 minute is made of 10 minutes.
just 1 second. Yes. So if you see the this is one of the runs. If you see, it defines the system details, what we have plugged in as the parameters. It defines the scenario of the system we have chosen. It defines the simulation results also. It gives you all the details of the simulation result, and you can use this result for the analysis. I think.
Okay, I think we are missing the question. Yeah, people are leaving now because they have another appointment at 3. So thank you very much, Mr. Parviz. I think it was very interesting. I understand the amount of effort which was put to prepare this presentation. So we have one question here from the audience. I will leave you to answer, Mr. Jabbar, saying, would the results be impacted by weather conditions? If yes, can you simulate weather effects on SEAMCAT?
Sorry, can weather conditions?
Again,
yes.
Would the result be impacted by weather conditions? If yes, can you simulate weather effects on SEAMCAT?
Yes, there is weather condition, but this particular tool does not consider the clutter and weather condition. It takes only the types of the geographies and type of the environments.
Okay, thank you. So other questions? Anybody from the audience have a question or would like to comment, or anybody has a question? Okay, if there is no question, any question? If you want to have a question, raise your hand, or so we can give you a chance, or type in the chat. Dr. Anas is saying, does it consider fading?
Yes, it does consider fading.
Yeah, the channel model itself, we have lots of channel models which of course consider fading. So yes, those channel models have all the parameters required for fading. Of course, yes. The answer is yes. I think Dr. Anas is a fantastic tool. It can be used for projects. The idea it's a free software. The idea it's also used by most of the European countries in interference analysis. It's also used by our project with CITC, so it has the advantage of being free and being very practical. So hopefully you can find a use for it in other courses. I would conclude the session by thanking you for being here, thanking Mr. Pervez for his fantastic efforts in preparing the presentation, and hope to see you in future presentations by the Center of Communication Systems and Sensing. So thank you very much. We'll see you later.
Thank you very much.
Thank you, Dr.